Hello, and welcome to my IPDPS 2020 talk on scaling Betweenness Approximation to billions of edges by MPI-based adaptive sampling. My name is Alexander van der Grinten, and this is joint work with Henning Meyerhenke. We are both at Humboldt University of Berlin. We first discussed the definition of Betweenness Centrality. Betweenness quantifies the importance of a single vertex x in a graph G. It's defined by taking the number sigma st of x, the number of shortest st paths that cross a vertex x, and dividing it by the number sigma st, which is the number of shortest st paths of all shortest st paths. When this fraction is summed up over all pairs s and t, it defines the betweenness value of the vertex x. And on the right, you see a graph colored by the betweenness values of the individual vertices. Here, red vertices have high betweenness values, while the blue vertices have the lowest betweenness values. Betweenness is highly important in the analysis of social networks, but also in the analysis of other types of networks, such as technical networks or biological networks. There has also been an interest of the parallel computing community in betweenness centrality, and there are very fast algorithms to compute betweenness exactly. However, even fast parallel exact algorithms cannot scale to really large graphs due to the inherent complexity of the problem. In fact, there's a conjecture that no subcubic algorithm exists for betweenness centrality, and that is based on the conjecture that APSP cannot be solved in subcubic time. Hence, if we want to solve betweenness on large graphs, we have to use something different from exact algorithms, and what we will do is we will use approximation, and in particular sampling-based approximation. That means we compute a vector BC tilde instead of BC, which contains approximated betweenness values for all vertices of our graph. And here's how it works. First, we sample a number of ST pairs, a number of source and target pairs, and then for each ST pair, we sample one shortest ST path out of all possible shortest ST paths. Along this path, we increment the sampled betweenness values by 1 divided by the number of samples that we will take. Now, algorithmically, the simplest thing that we can do is taking a fixed number omega of samples. And indeed, taking a fixed number omega of samples is also what Riondato and Konaropoulos did in the algorithm that I presented on the previous slide. However, Borassi and Natal noticed that one can actually stop much faster if one also considers the sampled betweenness values, BC tilde, and not only the number of samples that we take. That, however, implies that to check the stopping condition of our algorithm, we need access to the full BC tilde vector. And for parallelization, that's a hazard because we need frequent access to the BC tilde vector and frequent synchronization. BC tilde contains one element for each vertex of the graph. That means for the largest graphs that we're interested in, just synchronizing B tilde requires gigabytes of memory transfers. And what we do in this work is we present an MPI parallel algorithm that performs adaptive sampling while avoiding this communication overhead as far as possible. So what's the basic idea? We want to sample multiple BC tilde vectors in parallel, so we sample BC tilde I vectors in parallel, and we can do that because we assume that the graph is replicated on all compute nodes. To actually aggregate the BC tilde I vectors to a single BC tilde, we perform a parallel reduction. That's not really surprising. And we check the stopping condition only on rank 0 because the check is actually fast enough. The check only takes a fraction of the time that the sampling itself takes. Let us first look at a naive algorithm. If you want to implement this procedure in MPI, what you could do is you could maintain one BC tilde P vector per process P, per MPI process P, and then you perform a non-blocking MPI reduction, which is called MPI reduce in the code, to aggregate the BC tilde P vectors. This algorithm works in principle, but it has a major issue. And that issue is that it performs poorly on multi-core machines. Why? Because it does not utilize hybrid parallelism at all. And that's also not easy to work around because in contrast to MPI, multi-threading frameworks such as OpenMP do not have non-blocking reductions. So we cannot overlap the sampling process and the reduction process on multi-threaded machines so easily. Now let's look at how our algorithm can perform such a non-blocking reduction even in the hybrid parallelism setting. We denote the number of threads per process that we use by large T. And what we want to do is we want to run the MPI reduce only in thread 0 in each process. While this reduction is in progress, we want that all other threads continue their sampling process without waiting for the reduction to finish. The key ingredient that enables this is an Epoch-based mechanism for non-blocking multi-threaded aggregation, and this makes use of a data structure that we presented at last year's Europa. As an epoch, we consider the time between two reductions, and after each epoch, thread 0 performs the following work. First, it aggregates samples from all threads of its own process into its BC tilde P vector, and then it performs the MPI reduce to aggregate the data across all compute nodes. Now between each epoch there's a barrier, and this barrier is defined by two operations, force transition and check transition, and in the following we will take a closer look at these two operations. First, force transition. Force transition is only called by the thread 0 of each process. It's a non-blocking operation in the sense that after it is started we can check if it's completed or not. And the complexity of the operation is mostly constant. In particular, it only grows with the number of threads of each process. When force transition E is first called by thread 0, it causes thread 0 to enter the next epoch, which is epoch E plus 1. In the diagram below, this is indicated by the black bar in thread 0. This is where the epoch transition happens, and force transition E is first called. Then the transition is in progress, and it takes a while to complete. Until it is complete, we can always check whether it's complete or not, which is what I mentioned earlier. Now the question is, when does the force transition E operation complete? And that is when all other threads not equal to 0 call check transition E. So now let us take a look at check transition E. Check transition E is only called by threads not equal to 0, and it's weight-free, which means that it has a constant complexity no matter of what the other threads do, and no matter how the OS scheduler decides to schedule them. First, check transition E is a no operation if force transition E was not called yet by thread 0 in the same process. If force transition E was already called, then it causes thread T to enter the next epoch, which is also called E plus 1 here. Now the crucial point is that because the operation is weight-free and constant time, the thread can just immediately continue sampling after it calls check transition E. It never has to worry about the aggregation itself or when force transition E completes on thread 0. Now after we've established the basic algorithm, let's look at some experimental results. The plot on the left depicts the parallel scalability with respect to the number of compute nodes over the best known shared memory algorithm. We see that the adaptive sampling phase has an excellent parallel performance. Indeed, it performs 16.1 times faster than the shared memory algorithm on 16 compute nodes. And that is because it exploits NUMA behavior in a better way. We can also see that the calibration phase, which is depicted in orange, does not scale as well. This phase is also needed to extract the final betweenness values, but especially for large graphs, it only has a small impact on the overall running time of the algorithm. If we plot the number of samples per time and number of processes instead, we see that the performance is mostly constant over the number of compute nodes, at least on a small cluster of up to 16 nodes. Let us now consider the scalability with respect to the graph size. In these plots, we see the time that we need to solve an instance divided by its size. And we see that at least on random hyperbolic graphs on the right, the time required to solve an instance scales linearly with the instance size. It can be argued that the random hyperbolic graphs are close to real-world graphs, and indeed on a real-world graph with 3.2 billion edges, our algorithm only needs 148 seconds, while computing betweenness for graphs of this size was not feasible using previous algorithms. In particular, for exact algorithms, it was not feasible even when supercomputers were used. Alright, let's summarize what we've discussed in this talk. Betweenness centrality is a highly popular measure for the analysis of networks. However, it is expensive to compute. For this reason, we extended a fast approximation algorithm to MPI. Our key ingredient was the Epoch Barrier that enables a non-blocking multi-threaded aggregation of data. We saw that by better exploiting NUMA, our MPI-based algorithm achieved a superlinear speedup over the best known shared memory algorithm. It can also handle graphs that are orders of magnitude larger than what previous systems could handle. Last but not least, I want to direct your attention towards NetworkKit, which is an open source performance-aware toolkit for network analysis. While NetworkKit itself is not MPI-based, our MPI-based algorithm was implemented on top of its data structures. So if you are interested in scalable network analysis or scalable graph analysis, be sure to check out NetworkKit. That concludes my talk. Thank you for your attention.